Oh, I'm on screen cap. Oh, okay. Turn this off for a second. Just want to get that chat window up here because it's not coming up. Everybody is here. I gotta fix this chat window. Get that chat window up here. It's not coming up yet. Let me get that figured out. Whoops, that was weird. Well, everybody is here. I gotta fix this chat window. Get that chat window up here. It's not coming up yet. Let me get that figured out. There we go. That was weird. All right. I think I can close this. Well, everybody is here. There we go. All right, everybody. Who's here? Turn my laptop back on. EMtron. So I got two screens in here. I'm trying to get it set up properly so I can see everybody and tune this car. This car doesn't have a lot of space, and he's got a cage in it, and the cage is impacting the ability to put the front seat back some, which is killing my ability to put my other screen up and have room in here. So what's up, guys? Video quality crispy. I don't think that's sarcasm. That's literal, right? It's good. All right. So what I'm doing? What is that? Oh, is that a screen artifact? What the hell is that? You guys see that? Oh, you guys see it too. So okay. Weird. All right. I'm gonna start this thing before the battery dies. Gotta do some idle adjustment to it. Just have a little weirdness. You'll see a little hunt here in the cold idle section. Now the thing with the EMtron is difficult sometimes to figure out whether it's doing it because the drive-by-wire is being a cunt, or if it's doing it because the auto control is just set wrong. So one way to check that is to go here to engine functions, drive-by-wire closed loop control, and then here we can look at the difference between the target and actual, and we'll see is it doesn't track very well. It's tracking somewhat, but it's the you'll see the target drops and the blade doesn't, and so the blade's not dropping, the target keeps dropping. Then all of a sudden the blade goes boom, big drop, and the target goes back the other direction. So that's kind of a pain in the ass, to be honest with you. The only thing about the EMtron I can say that I dislike about it is this: the auto control function for the drive-by-wire is just a total pain in the ass. The likes I have never seen, and for some reason each car is different, and so each one requires a bunch of different stuff just to get the idle control to work. So here's, I'm going to borrow a table. I think I already borrowed it from this other guy. Yeah, okay. So we're going to pull some duty cycle out right here. Save that. Now right now I can't see shit on the screen because it's an auto scaling window here at the bottom. This window auto scales, and so I have to wait for it to pass by, and then there we go. Now the scale's back in. I want to make the chat window bigger. Actually, this chat window looks a little small. I want to make it a little bigger. Let's see if that helps. There we go. Alright, that looks better. Now we should wish I could see it. That didn't work. I'm gonna get the chat window large enough so that I can. Well, that just stuck on the screen. Oh, it's this screen. Okay. Wow, that was the exact opposite of what I wanted to do. That is not working. I have a feeling you weren't here for the last one. The last stream had the exact same settings, so well, I'm sorry, the last tuning stream, I should say. The last one I did was in my garage. Yeah, that one was not working. It is not working at all. Alright, well you can see with that change in the feed forward for the EMtron, the auto control improved drastically, which is great. I'm glad that it did that. The problem is it may stay, it may not. I may have to do more things later on. Next time it gets cold, you know, you never know. It is really an interesting unit there. And honestly, it's doing the PID for the drive-by-wire is not something I've had to do much. Most systems already have a really good established PID control system built into it, and I don't gotta do shit. You know, AMs and even the AMs get it pretty freaking close. Adaptronic was really good out of the box. The Haltech seems to work. Link seems to work. I don't even know if you have control of the PID scheme in the Link. Like, I just almost never do it. Hey, Curtis. So, the fact that you have to do it all in the EMtron, I find is a little weird. And then every time I ask for help, they give me a different answer. They give me a different map, and the map has different values in it already. So, luckily, by doing it a lot, I'm getting faster at it. As you can see now, the target and the position are really close to each other. And as I say that, it gets a 0.1 error. But, I mean, that's 0.1. Question is, will it do it after I rev? Will it recover correctly? Looks good. Yeah, the RPM recovered quite well. Gotta wait for the TPS thing here to rescale. You see I have an error of 0.1. I can't bitch about that. Nope, now it's 0. So it's a really close error. And it's not doing any hunting right now. So that feed forward table might be pretty close to correct on it. Like this. So yeah, that works. Alright, so that's saved. I'll make sure that's saved in there. The drive-by-wire section's got a ton of controls in it. Let me show you. I have this calibrates, or stores the calibration. Like, here's just the PID control section, the closed loop control. This is the standard PID. Here's your proportional, there's your integral, there's your derivative, the P, the I, and the D. Feed forward table, that's what I'm adjusting right now. Min and max duties. I said duty. And then your integral limits. And I have a 0 deadband, so I'm being super picky with it. Which is good. I'm good with that. Alright, so look at that table on the right there. Holy cheese balls. Now that looks like a complete mess, doesn't it? Over here on the right, this green and purple looks really bad. But what's really cool about that is, since it is self-scaling, like I said, it's actually really good because it's staying so close within 0.1, looks like. And my TMAF and my speed density calculation are within 0.1 to 0.2. So that's really good. That's good. Now, what's not good is the fact that they are all high enough to give me a negative 10% learn trim. So that's unfortunate. But I do see that my map-based one is higher, and that's based on speed density. So I can go to the speed density one in the cell that we're currently in, which is going to be down here near the bottom. And I can lower that down to drop that air mass down a little bit. But before I do that, I want to verify I'm even using that. So my blend table here, looks like I'm using all speed density in this spot. I don't usually use all speed density. That was just something I've done during this tune in various points to combat and check certain things. This is not the first time I've adjusted this car at all. First time on the dyno, but we just got this thing running last week, and so all I did here was push it to use more TMAF calculation. And if you look at the Lambda, it goes insanity rich. So the TMAF calc is giving us a ton of fuel. Bam! And it's getting really, really, really rich. Now, how much of that is from wall wetting and how much of that is from acceleration enrichment? I'm gonna find out. Go to transient fuel, go to transient setup. So we're using TPS for transient fuel. That makes sense. I have accel enrichment and decel enrichment enabled, so that's good. Accel clamp table. I only got 10% fuel, 11% fuel clamped in here, so that's not a whole lot. Sensitivity is relatively low. 12 is not too high. This is decay, how fast it goes away. It's compensation temperature. I don't care about decel right now because that's not my concern. My concern is how fast it goes rich. So the question is he going that rich because TMAF is incorrect, or is he going that rich because speed density is incorrect and I'm hitting a load cell that I would never hit otherwise? So let's just check that really quick. Let's look at here. Alright, so I got a 91% VE right here at 1,000 RPM. Probably not accurate. If you think about volumetric efficiency, the chance of this engine ingesting 100% of its volume at 1,000 RPM is very, very slim when you consider the fact that the intake valve shuts 60 degrees or so after bottom dead center. So the piston's on its way up again. And at 1,000 RPM, there's no air inertia. There's no inertia of the air moving into the engine. It really is just trying to draw it in. So that means that it's pushing a little bit back out at bottom, so I'm definitely not getting 2.5 liters. And I'm really, really doubting I even have 9.1 liters, or 9.1, 91%, considering just how slow everything's going. So I'm gonna knock it down. 85. We'll go 85 like this. I'm just gonna knock down that spot next to it. That was the wrong button. I don't know what I hit, but apparently I swapped the axes on the map. I don't know what button I hit. I hit Y. That's weird. I was reaching for R and somehow I hit Y. Alright, well there you go. Alright, so let's do this again. I'm going to log it. Or I'm not going to log it. I'm going to look at the air mass on the right here. I'm going to tip in. Really rich. I'm actually going to go to the logger this time so I can see it track better. Air mass is here. Hit F8. Start the log. Car dies. I just go to the floor with it and see what happens, and the car dies. So I've got way too much air mass going into the engine, or these calculated air mass going in the engine. So what do I have? Throttle air mass is really high, and speed density air mass is really low, right here. So my throttle calibration for air mass is not correct for this. And I don't know why yet. I haven't done any throttle body stuff on it, but let's see. This area table looks pretty normal. Okay, so it's not that. 60 millimeter, we got that. Version 1.1, we got that. 17, that's about right. That shouldn't be any more than that. And those numbers all look good. Huh. Well, let's look at our run times for the boost and make sure that that is accurate. Boost pressure and manifold pressure are within 1 kPa of each other. They should be exactly the same right now. The engine's not running, they would be the same pressure. And the exhaust manifold is 5 higher. That's weird. Exhaust manifold pressure should also be equal. All 3 of those should be equal right now. So the fact that they're not tells me I got a few things I need to tweak. Atmospheric pressure here is about 93, 94 kPa, which we have on the boost and the manifold pressure sensor. But the exhaust manifold pressure says 100. So I need to tweak that a smidge. So it's not an ADV. Found that out. Oh, this doesn't have EMAP. That's right, this car doesn't have EMAP. That's why. I gotta fix my yeah, exhaust manifold pressure, nothing. I don't have EMAP. So that means my fuel map. Do I have that set right? Oh yeah, that's just pressure. Okay. So we're good there. So that map doesn't matter. It's weird that it's that. Huh. Okay. So boost of that guy. That's really close. Let me just double check. Oops, wrong one. So the check-in is that I have all the right things selected. Like I said, we just got this car running, so this is a fresh install. This morning, or this afternoon, early afternoon, I worked on just getting the CAN bus stuff to work, getting the cruise control buttons to work, so cruise works, all of that. Getting the tach to function, because the tach wasn't working, and all those things. There it is, that one. Turned off. Just make sure. Yes. Okay. This Lambda's in the exhaust pipe, or in the down pipe, so I don't need EMAP compensation, which is great. So that's good news. I haven't seen the chat move at all. I don't know if it's not working or what. See it there. good. Okay. Thank you for responding. Just want to make sure. Boy, my allergies are fucking killing me today. Holy crap. Okay, manifold pressure. Where's my T-map? Boost pressure. It's 3.5. That helped. There we go. I just never calibrated it. I gotta blow my nose. I need Kleenex. Ow! Fucking roll cage on the knee. Both these! Ah! Ugh. Why hit just one knee when you hit two for twice the pain? God damn it. Okay, so that's calibrated. Now that's not going to fix it. That's a small change in the T-map. So I got to work on that a bit. So what we do here in this situation is I got to verify that it's T-map that's wrong and not speed density that's, you know, off. So we go back to tuning here, go to fuel model blend. We zero this out. All zeros. Now, if my acceleration enrichment is set up correctly, this means two things. One, I'm using only the speed density model in the ECU. So my air mass final and my map air mass are supposed to be the same, but they're not. They're close though. Alright, let's log this. F8, log is active. Alright, so we have our total air mass 0.7, our map air mass 0.67. Oh, I know why. I know why they're not exactly the same, because this thing has ethanol in it. So we're using both tables 1 and 2 right now. They're blended a small degree of blending. Stop it. That. Okay, so if I take this guy, just copy this section to the table 2, and then paste it like that. Then when I go to my logger and I log a blip, it should be almost the same. They're closer, definitely closer. All right, but see, it's TMAF. Woo, look at that, told me for bomb. TMAF on the other hand is a huge spike. Weird that it's so big of a spike, because this configuration should be really close. The throttle body, typically for this mode, about a 20 is correct. Typically, about a 20 is correct. Let's look at it again. 8. Still high. Still really high. I mean, that's 4 times the air mass of the speed density. Now, I don't know how close that is. Let's go to the tune and look at it. Lambda is really close. The target right there. It's even still a little rich. It's pulling some fuel out. So it's still pulling fuel out during the tip in. Okay, well, it's got some idle already. tip-in happens, it pulls less and then more after a period of time. So it pulls right here is a toe point. Okay. In an ideal world, you get this set up right, you don't need any acceleration enrichment. But that ain't cutting it. This is the other thing here. If I said 1, say 1, just to show you the difference. So we're going to logger, hit F8, turn it off, go to air mass. Let's see here, at the very tip in, a lot, but look at it lays right down on top of this guy. It's actually less, which means it's a little too much. That tip in, big transient. So for that transient is so large, we should probably add a little filter to it, because this is more the steady state of what the value is. There should be a little bit of spike because you get a transient, but that much transient is just way too much. So let's go here, see how much filter we got. We got a 10 on it. That's a decent amount of filter. I don't know if I want to put too much more than that. And then .998. Let's do that. Go back to logging. And as I adjust this, it'll slowly pick that TMF up a little bit. Let's do it again. So here, picks it up a little bit. Still a big spike. 37. But it starts to level out. Decent sized drop here. Log. Drop this back down some. 2.5. There we go. Alright, so wide open. Once it's stabilized, I hate that. Once it's stabilized, it's pretty much right on top of our speed density. So that's really close. The spike though, still tremendous. But what's cool about that spike, so let's say we keep that spike in. Gosh darn it, I keep doing that. Keep that spike in. If we go to transient fuel, and I just say I turn off Excel enable. Now, it's going to stumble like crazy. It's supposed to stumble like crazy, it doesn't like crazy. Why did that happen? What's going on here? It should just fall on its face. Let's go back to logging. Look at it. Check this out. So there's a loop transit time with O2 sensors, right? And you can really see the transit time right here in this log. So when I first tip in, you see manifold pressure here goes up. Immediately, bam, pressure goes up. So let's look at the time signature on that. Where's time on this? 1.630-ish, okay? But the O2 sensor doesn't register a change until here, 1.9-ish. So we're looking at 0.27. Is that about right? 3.9, yeah. About 0.27 seconds, or 270 milliseconds before I get a response at the O2 sensor. That's pretty significant. That's what happens when you put it in the downpipe. So that's actually good data. Let's put that in right now. Wide bands. I have Lambda transport delay. Looks like I got pretty close. I got it set at 312, so it's actually pretty close to what it should be, and that's probably why the air-fuel ratio is so darn stable right now. It's already set pretty close. So I'm gonna go down to that. I'm just gonna blend this right here. It needs to be correct. You gotta measure to all these points, RPMs and all that. Efficiency calculation, that's got to change because that's not correct anymore. I want this to be, I want it to be air mass, not this one. I want this one to be air mass. That. There we go. Oh. Housing. A2. Just a regular sized housing, nothing too fancy. Something that gives us good response, not targeting all the top end power. Dry sump system, yeah, I'm excited for it too. I got a little bit of work ahead of me before it's ready to be tested, but I got to change one of the bearings out in it. I have new gears from Subaru coming. Right now it has used gears in it. It's got one new gear and 2 used gears in it. I have new gears coming. So I gotta do that. I gotta add some sealant to the separator plates, and then I have to get the fittings that plug. Oh, actually, I already have those. Yeah, I already have the fittings for it. But then I have to get the electric motor that I want to run so I can run it on the test stand. I got to create a test stand for it and do that. So still have some things ahead of me on it, but it'll be a good time. Travis says, I can't say I've seen that in other standalones. Some do have it. Some do have a loop transit time. Some call it feedback delay. So I think Link might call it feedback delay or sample delay or something like that, but it's the same thing. Those are usually a single point, not always a map, a table like this one. In reality, it would be a table because as RPM and mass go up, I have more mass leaving the engine, and as everything speeds up, the delay time goes down. But typically you're running closed loop outside of the power band anyways on most other vehicles or most other standalones, and so you're going to be in a vacuum region anyways at a lowish RPM, so a fixed value transit delay or transport delay isn't that big of a deal. And this one though, we're running full-time closed loop through the entire power band, and so I want to make sure I have a relatively accurate transport delay so that when it makes a change, it doesn't start to ramp up because it's not seeing the response, and then that just creates an oscillation. And I don't want that because that oscillation isn't just in one direction, right? One side's rich and one side's lean. So I don't want an oscillation in the lean direction, have the engine run unnecessarily lean. So I want the transport delay to be somewhat accurate. So I always screw with this a little bit near the end of the tune. Right now I know I got this lower area pretty close, at least close enough that the system's response time and sample rates and filters are going to be enough that it's going to be pretty close. Single scroll, yeah, single scroll T3 V bands in and out. It's on the turbo kit that Lane and I designed on my car originally. This is the car that has it. It's got my up pipe flange, which is a 2-bolt flange, but it's pretty sweet because I got like this ridge in it. It's thick, but it's not so thick you can't use the stock bolts. But then it's got a ridge in it to increase the rigidity of the flange to minimize bending and stuff. But hey, by the way, Connor, I didn't say thank you. Thank you for the donation, man. I greatly appreciate it, and you know that money will start going towards it. Another one. Wow, thank you. Will the AFT start regulating standalones? The EPA? You know, I don't know the answer to that. I mean, they can't. They can make it illegal to use on a road car. And now, whether they can strip it out of your car, I don't think they can do that. Like, that's your personal property. You're not. It's not like a felony or some crazy thing, and they can confiscate your shit. But they can definitely choose to fine you should they choose to do that. But you know, this car's caged, as you can see, so it's clearly only a track car. But thanks again for the donation. I appreciate it. If you saw my oil pump one, which I assume you did because you mentioned it, that was a big kick in the wallet. So I appreciate any of the donations you guys are willing to provide. Thoughts on this turbo? I have G30-770 going on my right on, man. So I'm trying to think if I've done a lot of 770s. I've done a ton of 660s. I really like the 660. But I often feel like it could use a little more top-end power, and this 770 might be the ticket. So I think that it'll be awesome. Yeah, Travis, you know, what's funny about that is you're pumping fresh oxygen in that thing, you know? But it's more fuel and more oxygen, so it's more, you're like artificially increasing the fuel consumed by the engine. I say artificially, I mean you're doing it, so it's not fake, but it's like you're increasing the displacement because now the engine draws in more oxygen per stroke, so your effective displacement goes up. And if your effective displacement goes up, then so do your emissions, and so does the EPA's panties. But yeah, dude, this turbo I think is pretty sweet. I know the 660 is really good. I did the 900 on Josh's car. Like I said in the previous streams, I don't think the header and manifold were correct for that turbo. But it was only turbos available. The 660s and 700s or 770s were back ordered everywhere and like nearly impossible to find. So, all right, I'm gonna go back to this VE section here. Let's see what VE we got at idle where we're operating. This car is on stock cams, and so I'm actually surprised that the VE is this low, or needs to be this low. Right now I'm on ethanol, and there's a blend of ethanol in the tank, so I have to adjust both of these VE tables here. But yeah, the fuel trim's still really high. Let me just double check and see if I did the fuel density. There it is. Now, is this table correct? Is this the... Did that help or hurt? It didn't help. So is nitrous. Yes, also legal. No, I meant standalone's being illegal for a street car. Yes. Oh, okay. You're on board now. Fuel consumption is fake news. Yeah. If only... I'm going to spit this gum out. I'm smacking my gum here and I hate it. Alright, so I'm going to hit my run times here. I'm going to figure out what the heck's going on. I feel like I have a big trim, and the trim seems too high. The trim seems too high for the ethanol content and the VE that I have in the table. So I want to figure out why that is. Main VE tables 52 and 51, but final is 57. So I have something adding 7 or 8% to it, which coincidentally is really close to what's going on here. So let's see what I have for corrections on here, see if we can figure out why we have an increase in VE. Looking for trims. Here we go. Mass air modifier, 7%. Okay, do I have 7% in here somewhere? Air mass modifier. Hey, look at that, 7%. Well, I'll be dipped in shit. Let's try that. Zero. All right. Look at that. That's a lot closer. Now we're at 5%. I like that. So these are ID 1300s. I don't know if I have the correct size put in there on that. Says 1335 at 43.5. If I put that in, it's going to get worse. That's if it's an X2. If it's an X, it's 1345 at 43.5. So I need to put one of those two values in there based on what the trajectory it is. But when I do that, it's going to get even richer. So right now I have it at 1300. And that's a 300 kPa. What's 300 kPa? Is that 43.5? I mean, I think it is. $44. So 2.95 kPa, or 295 kPa. Oh man, it's way off. Yes, that's correct. Maybe you did that after there's a stream delay here, so my guess is you're inputting that comment and then I say that and then you're like, son of a bitch. So I have a stream delay on there. I don't know why OBS has a delay inherent to the system, even though I didn't tell it to. Oh, I gotta get rid of this too. This is wrong. No EMAP sensor. So no more expansion ratio. I do have a fuel pressure sensor on here. I should. Let me double check that really quick. 3. Search, because there's so many freaking menus. Fuel pressure. Right here. 305 is my current differential. Okay, so there's definitely a sensor fitted. Alright, let's see how close we are now. Now we're adding 4%. Excellent. That's actually good. Because, like I said before, I was surprised how low that VE had to be. And now I can add that little bit to the fuel injector, and that's going to help too. back in. Because usually these are like 55 to 60% on factory cams. And not having that seemed a little weird. There we go. Alright. And we got 3%. Now I'm happy with that. What's up, dude? Nightfire37. I forget your actual name. Sorry about that. Can't remember everybody's name. Alright. Finally. I can't believe it doesn't fall Lena's balls. I mean, I do still have a lot of VE in here at atmospheric, so what we need to do is we need to somehow get there. Let's get in that spot. See what VE's action. Oh yeah, slip that clutch. Alright. Here I have 1,000 RPM. I'm going to put it to the floor. You can see it's still pulling 13% fuel out of it. So let's make this down to 86. So I got the dyno holding the car at 30 miles an hour, and this way I can put it at, that's exactly 1,000 RPM in 6th gear, and I can give it lots of throttle and wait for the fuel to stabilize and figure out how far off it is. looking at it, I don't know if you can see it really well or not. You can see I got 60 on the right side of 82. It's not super common, right? So what kind of things would cause the VE to go down so drastically at only a change of 250 RPM for the same load cell? So what kind of thing you think that would, what kind of thing would cause that? That's obviously significant. I mean, I got, was that 16% difference in volumetric efficiency in that load cell? That's a big freaking change. Why would it happen only 250 RPM, but the exact same load? And then if you go up a little bit, we got about 5% difference, a slightly higher load, and almost the same at atmospheric pressure. So that's like, but that's still down lower. All of a sudden, I have 83 at 100 kPa, but then I also have 83 at 60 kPa. That's interesting, right? Like, what do you think would cause that? Now I know there's a stream delay, so I'm not going for the entire time. But I'm gonna tell you, one of the biggest things is going to be intake resonance, and then the other one's going to be cam timing. So let's look at our cams, engine functions, VVT cam control, target table. So at 2,000 to 50, what was I at on the fuel map? Let's go back to the end, double check. Where was I at? 2,000 to 1750. Okay. So I'll go back to the cams. We can see here at 2,000, I've got 20 degrees of advance, and below it, one cell, it's not the same RPM, but it's close, I've got half of that. So I did it at 60, so half of it at 60, and then at 100, a half of that. So we have a combination of cam timing and intake manifold resonance that are both playing a part. Now what's interesting about that is the cam timing reduced my VE, and that kind of sucks, right? I don't want to reduce the VE of the engine unless I'm intentionally trying to reduce the VE so that in cruise I get better fuel economy. Now you may say, wait a second, what? The idea is, if I put enough overlap and I adjust the cam position correctly, I can make the engine have a lower VE for the same throttle position or the same manifold pressure. So what I'll do is the car will then make less torque, which means I give it more throttle, which your brain says is going to consume more fuel, but it won't. What it'll do is raise manifold pressure a little bit more, and that will reduce the differential pressure across the throttle body, preferably eliminating manifold vacuum almost entirely. And that, by eliminating manifold vacuum, you reduce the vacuum that the pistons are feeling, and you reduce the amount of power lost pulling the piston down the bore. So what am I doing though when I'm adjusting those cams? What I'm doing is I'm increasing the amount of retained exhaust gas in the cylinder. I'm not pushing as much exhaust out. I hold more exhaust in, and by holding more exhaust in, I draw less fresh air in. And if I draw less fresh air in, I have a slower burn. I have less fuel to put in there because I have less oxygen available. So I put less fuel in there, and the car makes less torque. So then I have to open the throttle some more and raise the pressure to get a little more air in. And so the idea is to get the same amount of air and torque out of the engine in cruise with a higher throttle position, and therefore reducing manifold pressure or vacuum, increasing the pressure, reducing the losses, what are called pumping losses, when the piston is sucking on the back of a closed throttle body. So in essence, I'm making the car more fuel efficient in that region, and that's great. You get too aggressive with it though, and you make the car super sluggish. If you do it all the way to atmospheric pressure, then when you give it full throttle, ask it to go somewhere, The cams were already in a spot at atmospheric pressure. Nothing changes. The car has no power until you get out of that cell, and then everything starts to happen again. So you got to be really careful about how much you put in there. This might be a smidge excessive. Now, this car is quad AVCS. It's not just intake. This car is exhaust too, and so the exhaust AVCS is also playing a part in that. And if you look here, there's a huge change right there. And so that's probably where it's at. It's probably all on our exhaust. Look at that difference. 10 to 31. It's a 10 to 38 between those two cells. And that's almost, that's 18, the other one was 1750. So that's going to most likely be our biggest drop in our efficiency. The exhaust cam is being retarded so that there's a lot more exhaust going into the cylinders during overlap. If I take this and I make this 10 as well like the other one, I bet that VE goes up. I would think. That's typically the way it works. Yes, the perception of sluggishness will also be there because you need to move the pedal more. That's correct. Alright, so I moved that exhaust cam now to the same as the 1800 RPM spot next to it. Let's see how much of that VE difference is based on the exhaust cam. Let's go to the fuel table here. Now I can tell you already, it feels less sluggish on the throttle. It's definitely getting more air. And if you look right now it's 15% lean. So you can see how much that exhaust cam had a huge difference in it. I'm 15% lean now. That's a huge difference. Look at this VE I gotta put in here. It's just counting up right now in closed loop. A little more. That went up. That's a huge difference. Now I can tell you, I can feel it on my foot. I can feel in the response of the engine that it is improved. So what do I want to do? Yeah, that's really good. So I immediately driving the car felt the difference as I passed through that zone, and you can see the VE jumped up from 60, what was it, 66 or something, to 78. So we picked up 11-12%. Actually more because I'm doing this here still. So yeah, so a huge gain in VE by adjusting the exhaust cam, and that makes sense, right? If the exhaust cam is retarded a lot, the intake valve opens up, the exhaust cam is still open as well. Through overlap, I suck exhaust into the intake manifold, and then the exhaust valve shuts and I suck the exhaust in and then fresh air on top of that. And that lowers the displacement of the engine, lowers how much fresh air I draw in, therefore lowering the volumetric efficiency of the engine. And here you can see how much, I think 13% difference in just a 20-degree change in the cams. Not that that's a little bit, that's a significant change. So now what I can do is I can go for the same effect now, but also increase compression. So instead of using the exhaust cam to get all that overlap, I can increase the overlap on the intake, which pushes the intake valve open sooner, hopefully when the exhaust valve is still open. The benefit I get from this is I do lose VE, but I increase compression. So for the same volume that I'm drawing in, I also get more compression, and that means more power output for the same air charge. So I'm increasing torque by doing so. So now let's go. I'm gonna make this. Let's make this column here. Let's just make that the same, like that. Now let's go back to that fuel map again. Now it should get too rich now, and sure enough, now we see we're 4% too rich. Too rich. Too rich. torque output for the amount of air that's in there, which means hopefully I didn't lose as much torque. Sorry, I'm looking at a few things. I didn't lose as much torque as I would have from just the cam timing change, or the exhaust timing change. Now the benefit of that is that it feels snappier on your foot, and I can tell you it's snappier right now, which is weird because it's got a reduced VE, yet I can tell that it's more responsive than it was. Smarter, tune it for power, but use the VT offset table for economy when the throttle is closed. Well, not closed, but yes. So, if you look at my VT table, they call VT in here. I have it set on manifold pressure. I don't like that. Okay. The reason it's set on manifold pressure because that's the same axis the fuel table is set at. I don't want the cams to be at different amounts or different advance or retard values at the same spot on the fuel map, because we just saw how much the cam timing changes the VE of the engine. Like we saw a 15% swing in 20 degrees on just one of the cams, and then another 5% swing in a 10-degree change on the intake cam. So we can make huge swings in VE, which means in a speed density setup, if your O2 sensor is a little slow or located in the downpipe, you create a car that has hesitations to it, a little hesitation, and then goes right as the O2 sensor picks up, because the cams are different spots at different times. We don't want that. We want the cam position to be the same axis as the VE table, so that when the cam is at that spot, the VE is already the same for those two things. Now, I don't like doing it like this, because I like to have EMAP. I want to have EMAP compensation on every car I tune. And the reason for that is cam timing is very much about not just RPM, but the pressure difference, the pressure ratio across the engine. Manifold pressure of the exhaust, manifold pressure of the intake. That pressure ratio has a huge effect on where I want my cams to be, because the cams are affected greatly by that. So let's say I go into a bunch of overlap like I had earlier. If I have a really positive pressure ratio, meaning that the intake manifold is a lot higher than the exhaust, then what's going to happen is the air and fuel is going to go from intake to the exhaust and out the tailpipe some. And I might not want that. I might not want to stick raw, unburnt fuel in the exhaust pipe. I don't know why you really want to, but you could do that. It would increase cooling in the cylinder quite a bit, but it would totally screw up your O2 sensor readings and your EGT readings. You'd have a hell of a time tuning it. Which you could potentially correct with changes to injector timing, but in higher load cells, when the injectors are firing for many, many degrees, you can't do it. If you're in cruise and you're just firing for just a few degrees, then you can do that. So now, what do? Well, I have to do a manifold pressure. But with EMAP again, let's go the other direction. Now say exhaust pressure is higher than intake pressure, like in cruise, and I go into overlap, the low pressure of the intake is going to draw some of that exhaust in, right? So I get the air in the engines go in the opposite direction, especially at low flows. At high flows, I still have inertia on my side, and it isn't as obvious. But at low flows, there's not much inertia in the charge, especially when it's a low density charge. I'm in vacuum or just barely at atmospheric pressure, and the engine RPM is low. That overlap effect, polluting the intake port with the exhaust, is going to be very dominant. In this case, we saw that. We saw how dominant it was. There was a lot going on. And so ideally, I would have EMAP in with my cam timing, so that when the exhaust pressure was higher at my whatever target RPM I wanted it to be higher, I could put a bunch of overlap in to reduce the VE and you get really good fuel economy. But then when I give it more throttle and boost starts coming in, then I can go the other direction with it. I can start pulling that exhaust out of there so that I reduce overlap and I don't have an issue where I'm putting a bunch of exhaust in the intake at high boost. Because typically at high boost, the exhaust manifold pressure is higher, and I want to get good overlap flow if I can through the engine. And in order to do that, I got to have the exhaust cam timing and the intake cam timing correct based on that pressure ratio across the engine. Hope that makes sense. It's kind of convoluted. I see somebody on my screen. What's up, dog? Oh, okay.
Just gonna get a few shots.
Okay. Right now I'm on VE map tuning, so I could do a little mini poll. It's gonna be rich as balls.
It doesn't matter. I mean, I can wait.
Okay.
I just figured, Tony would probably want a shot or two of this car.
Oh yeah, probably. So instead what I have to do, so I don't have EMAP to know what the pressure ratio is, I have to make some assumptions. I have to say, well, at atmospheric pressure, I'm not going to have higher exhaust pressure than intake. That's just not going to happen. It's not going to happen because I don't have, one, any pressure between the engine and the turbo. There's not enough back pressure on it. There's not enough flow through it. So I know that in this spot right here, that's fine. But now at 160 kPa, I might, but 160 is not much. It's not even 14 pounds, and this turbo should be way more efficient than that. So in this map right here, I don't have anything, I don't have any good numbers in here where I would potentially have whoopsie, shiza, where I would potentially have pressure issues. So I want to change that. So I want to go starting value. I don't want it 0 because I hardly ever would be at 0. And then we'll do this at like 30, and then we'll see what that gets me. And that's too much. I think I can work with that. I'll try 20 real quick. Yeah, I can work with that. Okay. So now what I'm just going to say, I still want the 45. I want this column to be down to my 100, like so. And if I want to kill that VE in cruise, these cars cruise between 30 and 35, or 300 and 3,500 RPM. So I can do this, get some of that VE droppage and fuel economy action here. But at these higher pressure ratios, I know that the exhaust is going to start to be higher. This should be 0. And so what I'm going to do is lower these at the higher RPM. I will fix that right here. And then I will bleed this into about this point here. So now what happens is, as the boost pressure goes up and the exhaust pressure goes up, when it starts to clear the boost pressure, I'll start to have a reversion, flow reversion. So now what I'm doing is I'm using less intake advance to reduce how much of that exhaust gas I'm polluting the intake port with. I'm going to do the same thing on the exhaust side. I'm going to change the exhaust side too in a similar manner. Whoops, I don't want that. Cancel that one. Sure, you can turbo there. Okay. So I want this to be 0 here. I actually want this to be 0 all the way across, right there. That's a lot of reversion going on right here. That's going to give us a ton of exhaust gas retention in cruise. And then in spool area here, a lot of overlap can often help with spool as well. There, but that's okay. I'll adjust that in a second. That's alright, actually 0 is good. That's a weird one. something like that. That's just a starting table. I got some stuff I could clean up on it, obviously. This spot right here, and a few of the spots I can clean up. But the idea is that the light loads in cruise have a lot of reversion. As I add throttle, I maintain some overlap. This is too much right here. I should reduce that. Retain some overlap to help turbo spool. And then as exhaust pressure goes up, I'm going to pull away that overlap to prevent me from retaining too much exhaust gas in the cylinders. So that's about as smart as you can make it. If you have EMAP, you can make it really smart because it knows what the pressure differential is, so you can make it do what you want to do. probably saw, I was maintaining just about atmospheric pressure. Slightly, it went up a little higher than that, a couple psi, due to dyno loading and the fact that my throttle was, only backed off so far. As it is, though, the fuel correction still a little rich in those, you bastard, in those regions. Here's the Lambda target, the white line. Lambda pink is what the Lambda was. Ignition timing is down here. Here's our fuel trims. They're all a little rich. Richest being in this spot right here. Let's go to the fuel map. Let's see where that is. Hit O. There we go, up here. So yeah, that's in a little spiky area. It goes up 103. Goes up quite a few percent in just a couple of cells here. So that tells me that that's too much. Percentage change, that was, what was it? 9%? Is that what I needed to do right there? About 9%, yep. So I go 0.91 times. Well, that'd be great if I had the cell selected that I wanted to do it in, but I didn't. Try it again. There we go. 0.91, shift 8, like that. Adjust a few things in here. Smooth some areas out. So when I pass through those areas, I'm having big transients, and then I can make smaller adjustments to them when I get there again. Closer to where the VE is or has historically been. Alright, now I can hit these cells again. Let's see how much closer my trims are. Before I do that, let me just look at timing again real quick. I got no engine noise, which is expected. I had almost almost no load on it. I had rich AFRs and no boost, so almost no noise. That's good. My threshold's probably a little high then, because the sensors are way down here, my threshold's way up there, so I will probably either raise the sensitivity of the sensors or lower the threshold. I'm going to start with the sensitivity of the sensors. Get 20% more sensitivity out of them so I can hear that engine better. Oh yeah, it feels nice. Feels good. So I got those cylinders a little louder with the increase in the gain on the sensor. Still nice and smooth though, I like that. Back to tuning here. Look at that manifold pressure. That's my foot, I'm backing it off, watching it track across the fuel map right there. That's what I was trying to do, trying to get it smooth. Fuel trims, much closer. You see here in the middle, I got 4%. 4%, where's total? 1% total, 2% total, 2%, 4% total, 8% total up top. That's expected. I didn't drop the VE near enough up top, which I knew was going to be the case. I just didn't want to go ham and make it go lean on accident by pulling too much out. But we see now that it definitely needs a drop. So let's do that. Let's drop the VE some on the top end. A lot. It's a big change. Might be too much. Put a little back in right here. Right about there. Try that guy. Now I could use my AFR correction to get the exact amount right now, but it was growing still. I hadn't even got to the correct air fuel target yet, and since it was growing so much, I'm just going to pull a bunch out and then hit it again, and hopefully next time it'll be closer. Hit the pad with my thumb. Technically, at 0 RPM, you get 100%, but obviously we're not getting 100%. Down here. We'll smooth that out for now, until we get in there again. Alright. Now, the VE map should not be smooth everywhere. When it's done finally, it will not be smooth everywhere. But right now, I just gotta get everything closer, so I'm making small changes. you can see air fuel still dives off a bit at the end there. Still dives off rich, and the closed loop is starting to pull more and more out of it. But now we're within 3% to 5%. Shoot, we're basically 3% or less everywhere at this point at these manifold pressures. I got 4% right there at the onset of the pull. So, all right, that means that we're getting close on our VE curve values at that pressure. So now I can start adding a little bit of boost to it and see how much the VE goes up by how lean it gets above this pressure. Before I do that though, I'm going to make sure that I have my boost controls turned to 0. I don't think it is. Closed loop, yeah, we got closed loop, that's good. Initial position, it is 0 at up to something pounds. I'll make it 0 across the board here. There we go. The wastegate duty cycle will start at 0, and then we'll go to closed loop control and integral. Well, we can 0 that out, but let's just go 0 on max duty. There we go. I don't gotta worry about it. Okay, let's see what that does wastegate. Sounds pretty cool. That's a cool exhaust note. Wow. I forget what header's on this, but that exhaust note sounds really good. One of the things that we did with the turbo kit was bring the turbo down so that the downpipe was straighter, and I wonder how much of that affects the note as well. Instead of bending the pipe, having the sound waves bouncing and trying to cancel out, getting more of a straighter downpipe. That actually sounds really neat. Definitely sounded meatier and throatier than a lot of other ones I've heard. All right, so we were at almost 14 pounds on the dot. Now this is on ethanol, so when you see this timing saying 18 degrees, you don't go, holy shit, that would be too much if it was on pump gas. But it's on 40% ethanol right now, so that's actually fine. Now we do have some negative trims here though, like we're still pulling 9% fuel out on the top end here, 10% there, 8%, 5%, 3%, 4%, 4%. So pretty close through the mid-range. Only over 5,000 does it start to stay too rich. See what our cams look like right there. Maybe there's a cam timing adjustment we can make to aid in that. Not really. That's a pretty good spot, really. Got getting really low in the cam timing position. 10 degrees. That's not too bad at all. I could probably go 0. That might help a smidge. And the exhaust is already coming up too, so really the cam timing looks pretty damn close for what we would normally want in that situation. It's interesting though, I got a little bit of jitter here on this exhaust cam. See the solenoid going right here, and you can see it on the left hand cam. So the left hand's got a little bit of waviness there, and it's off the target. It's behind the target a little bit. Some waviness here between the target where it's supposed to be and where it is. The intake doesn't have that. Intake tracks the target near perfect. Look at that. But the duty cycle hardly had to change to do that. It's almost like it wants this curve, which is really interesting. This one though, duty cycle It doesn't change a whole lot either, but a little bit. But we can see here it's not tracking the target well. Not terrible, but I'll need to adjust that a smidge too. Have to figure out where we're at, like whether we got issues with the derivative being too high or what. So to recap, boost was great, super steady, super smooth. That was good. AFR was really close. It just started to get rich over 5,500-ish, somewhere around there. Yep, here's 55, starts to get richer and richer. So I got to pull some more out of the VE in the map there. You see it pulling, even with it getting richer, it's still pulling 10%. So quite a bit of VE has to go away. Oh yeah, this car's totaled. Let's see. What was I saying? So the fuel, got to pull a bunch of VE out because that fuel is still way too rich. Other than that, that looks pretty good. Got the knock screen. We're on 40% ethanol. There's no freaking knock, as you would expect. Timing was 18 at peak, at the onset of peak boost, and 22.5 at redline, which is low. That's actually really low. I could put a bunch of timing in it, and the drop in horsepower over 6,000 agrees with me. I could definitely add a bunch of timing into it at this load with ethanol and everything. Probably 4 degrees even by 7,000. I could add quite a bit in through here, and that should, in theory, raise the horsepower up. This thing thinks the power should be increasing the red line, judging by the airflow and the fuel mass. Now, that's not going to be correct because we saw already that it had to pull 10% VE out up top, if not more than 10%. So when I pull that VE out, I just did right now, there, Bradley, just for you. When I pull that VE out, that power curve is going to drop on the top end. And once I get to where that air fuel correction is almost zero through the whole power range, that power curve is going to look really accurate and really close to what's on the dyno, provided my timing is correct as well. So this is what the engine should make with the indicated airflow according to the VE map. That's what it should, that the power curve should look like, which obviously it's not, because it's wrong. The airflow is not right. VE table 2. Here, now you can see we're pulling a lot of VE out. Right? Oh, this fuel map only goes to 200. Oh, I gotta fix that. We're gonna go way more than 200. Did I use all the sites or just some of them? It's more than we're going to use. I probably didn't need to go that far. I don't think I can go 17.5 on these. I don't think it allows me to do decimals. Oh, it does. Okay. That's cool. I don't plan on that high either, but I should have went 12.5. That's what I meant. Alright, now it's going to ask me if I want to interpolate. The answer to that is yes, I do want to interpolate that because otherwise all my shit's going to be all messed up. I don't want that at all. I want it back to where it was. Okay. So it fixes, see my VE's the same here. Looks pretty good. Trim right now, total fuel correct 3%, 2.56%. Okay, I like that. So I've given myself more room on the VE curve, or on the VE map that I didn't have before. Now it's a much larger curve. In my log, I'm at 200-ish right here, and it says I got to pull VE out. Now what I'm going to do is actually I'm going to pull a bunch out up in this corner here first. So this corner here, I did that. I'll explain explain in a second. I'll pull a little more right here. Hey, thank you for supporting the channel. I really appreciate it. I definitely put it to good use, and I greatly appreciate your support. It helps me, motivates me also to keep doing this, but also it helps so I can do the R&D on the stuff, and then sometimes just buy myself a nice dinner. So thank you very much for that. How you can tell when you tune your perfectionist, decibels and the axis labels. Yeah, I suppose it's not necessary. Oh man, I was tuning my BMW and I was getting really irritated with it because I don't want to guess. I hate guessing on stuff. And I want to either calculate, you know, and anticipate the correct values and all of that. And the way that BMW system is, it's a lot of guess and check. Does this work? Oh, it didn't work. Let me try this. Does this work? Nope, that didn't work. Let me try this. I hate that. Like right now, I'm smoothing, right? So here, obviously, there's no calculating going on other than the interpolation scheme of the ECU. I'm doing this again, like I said earlier, just to get close to where it needs to be, so that when I hit these cells, basically what I want the air fuel correction in the log to be really close when I need to correct the actual airflow error. The problem is, as you're sweeping, combined with the time delay, that value has to respond to an error, right? It can't really correct it immediately. It has to run an error over time. Proportional is instantaneous. I'm already 0.7, well, at idle 0.7 or 0.27, and then up top, 0.0 something seconds behind. And then the integral, which is over time, has to build up. So the correction is only going to help get me close to my target. It's not going to get me at my target. So if I get the fuel map close enough, when I see those corrections come in, 3%, 4%, I know it's actually probably 5%, 6%, something like that. Instead of, I'm so far off in the fuel map, the error is actually 15, and the system just didn't have time to count up to fix it. So I'm bringing everything down, I'm getting it closer to where it should be, so that when I do pass through that cell during the tune, the correction is close enough, I can look at that and say, the computer did the math for me already. The computer did that math. It said it is 7% off. I know that it's probably 7.5% off. That's great. So I'm doing that now, getting it close. And that's why you see me doing these large bulk changes in areas. Just wanted to explain that. Also, the gas light's on this car, so I don't know how much ethanol I have left. Now, as a reminder, if you see these large fuel trims when I'm tipping in, like right there, see that the yellow and the red? I have acceleration turned off. So, acceleration is currently off, and since it's off, I get slight lean trends when I tip in. Now I can put the T-math back in it if I wanted to, down here at those areas, and put in like 25%, and the huge T-math spike would give me acceleration enrichment. Sounds really good, but that's not an usual Killer Bee sound.
Or is the up pipe?
I think it's the up and the down pipe being flatter that's doing it. It sounds really good.
It doesn't sound raspy like it usually does.
No, it doesn't sound like a Subaru either. It definitely sounds cooler. It sounds more like a Porsche. When I hear like the Carreras in their Carrera
Is it
racing,
on pump or what's the mixture?
40%.
Are you just starting to get power into that?
That's 14 pounds.
pretty good.
Yeah, 350.
Yeah.
350 on 14 pounds.
Sounded spicy.
Yeah.
For essentially for a stock, you know, no power adders inside the motor.
Right, just forged
Yep.
factory cams and stuff. Yeah. I'm almost out of fuel in this thing, so.
Oh, we have 2 gallons, two things of ethanol.
Okay.
Unless you want to pump.
I mean, I haven't done any pump tuning on it, so it'd be nice to.
I don't think he's gonna run pump gas because he's in Vegas.
Well, he's gonna drive to Vegas though.
Sure.
So need some of there. I mean, I would like to do the majority of the tune around 40%. That
You
gives
do
me.
or don't?
I do.
Okay.
I'm at 40 now. It's like the most around 40 because that gives me a good ability to tweak things or to anticipate differences. Now, would you grab that phone and when you pick it up, the screen will light up.
What?
The screen should light up. Okay, so that's my live feed, one of them.
Oh, I was wondering
So
where that
if
one
we
on
do
the-
this, we go back camera. If you would show the power curve. You can kind of see it. So you see the blue one is the 2 poles ago, and then the pink one is when we just did. Now, the power went up a bunch, but I didn't adjust the timing. Oh, you can go and just hit that button again, front, and then set it back where it was. And then it just looks to the side of the car. I didn't adjust the timing, right? Well, I did. Because my timing is based on air mass. So if you look at the timing here, ignition, 2, this axis is air mass. And this was intentional because air mass per cylinder gives us a load per cylinder. So the time's based on the load. So when I lowered the VE in the areas where the tune was, you know, at 10% or whatever, that reduced the air mass, which reduced the load, which increased timing. So timing actually went up. And if we go to the log, and I go to tune, you can see now it was 18.6, now it's 18.9, but up top, I added a degree as well. So 22 to 23 degrees, so I added 1 degree of timing. But the air fuel is way closer. See right here, it's much closer to that line. Still negative though, look at that. Still very negative. Still pulling 11%. That's crazy. But it makes sense. Because the stock cams, the VE is dropping like a rock. Power curve hangs on a little better as you saw in the picture. And if I reduce the VE up here correctly, what will happen is the air mass will drop off really quick, or the load will drop off really quick, and that'll ramp the timing up, and then we'll have a timing ramp that's more representative of what a Subaru usually has for a timing ramp. Do I always turn off acceleration for tuning? No, I did that earlier to show what was going on, but it does help to minimize transients while you're trying to check things. I can turn it back on if I want, or like I said, I could blend in TMAP. Which I'm going to do that right now actually. I'm going to put a little bit of TMAP in this area, engine speed, manifold pressure. So like this, go with 25%. Those small TMAF blends. Oh, I have TMAF up here still. We actually hit that probably during the tune, during the pull. And then now it's not as lean. It's not as lean, so I can add a little more if I wanted. So if I went like this to 50, then I would get a bunch of fuel from the TMAF, which it will be that way in the end when I get the TMAF and the speed density balanced. So now, watch the green line, that's AFR. When I tip in, it goes way rich because I added all that TMAF into it. Now if I zero that back out, let the car stabilize. Now we're here at that green line and I tip in, it goes lean and then rich, right? So you can see that the TMAF added fuel based on a big transient, which I showed everybody earlier. That was closer. That transient right there, this little peak, that's the air mass calculated by the TMAP system. So if I hit the throttle, you watch how high this number goes. It's way up there. Whereas the speed density calculation is much lower. It's down here. It's half as much. So, anyways. Not like a Subaru. Sounds cooler. Yeah, I know. I mean, you only tune Subarus for so long before they just don't sound that great anymore. Is doing dual AVCS a worthwhile swap? Are you single AVCS cam? Are your single AVCS cams better? The cams are the same. The profile is really, really close on the exhaust side between the two of them. They're not identical, but they're really, really close. They're near identical. Let's put it that way. One's adjustable, one's not. Intakes are the same, so the cams aren't changing. All it does is give us the ability to do some more adjustments. Now, exhaust cam timing has almost no effect on power. I did a stream a while ago where I changed the exhaust cam 30 plus degrees, and it had absolutely zero effect on the power output of the engine. Which is one reason why I hate the fucking Atlas, because it has a variable cam time on the exhaust. Like, what the fuck was Chevy thinking? On the exhaust? Morons. I think that's the only time you hear me say an OEM is a moron. I was talking about Dodge. Yeah, I can't really put fucking variable timing on the exhaust, not the intake. Like, you get so much more out of intake cam. So much more. So the exhaust cam is really good for cruising and affecting that stuff. In power, it has almost zero effect at all. So if you're only doing a power thing, then no, it's not a worthwhile swap because it ain't doing shit. Wow, the heater was on here. No wonder it's so fucking hot. No, it's not a worthwhile swap because you're not going to do anything in power. There we go, turn the heater off. If it's a daily driver, then it'll help your fuel economy if you care about fuel economy. If you just want it to be normal, you know, decent, like a EJ normally is, then no, it's not worth it. Because you got to use 2 more inputs and 2 more outputs. That's inputs and outputs are valuable real estate in a standalone because you want to do stuff with them. So, no, not really. Intake is always worth it. If you have a car without intake ABCS, I feel a bit bad for you, son. There's 99 benefits and you got none! I made that up just now. I bet you're surprised. Okay, so let's go back to that fuel map. I'm going to copy this table. And I'm going to paste that in table 1. So I think it's Control Alt. Nope, not that one. It's Shift Control V. Yeah, there we go. Alright. And then this is pump gas. It's got a couple percent less VE from the get-go. Just because they do. That's a conversation for another day. Alright, let's go back to number 2. Intake and exhaust are used for internal EGR. The exhaust just makes it stronger EGR. I think that's what I was explaining earlier, that the exhaust AVCS can give you a more powerful internal EGR. Boy, these stock cams fucking lose VE, don't they? Look at that. That is a fucking drop off. Let's see how close that is. still at 8%
How's it
up
working?
top. It's going good now. I'm almost out of fuel. Got him on the gas light.
Where's your outside view camera?
Oh, you're answering me on that. Oh yeah, for the cruise thing. I mean, the intake does it too, though. That's what I was getting at earlier. What?
Oh.
Right there. Yeah.
I was like, why do I see the back of me?
Yeah.
How's it working?
I've said good like 5 times.
Sorry.
It's okay. It's good.
Okay.
I'm just working on the VE curve for this boost level that we're at. Still high, which is crazy to think about it because I'm pulling so much VE out, but that's stock cams, really.
Yeah.
Where's my power and torque right here? There we go. That's starting to drop off here up top, just like the power curve is on the dyno.
Yep.
So starting to do what the dyno is showing.
Like 6,000-ish? Yeah, that's about right where it starts dropping. So 6. Hey!
Will you guys help pour this thing in? Can you pop that gas cap guy down there for us? Haven't got more pump.
Oh, sweet. Alright, so my air mass is a little low, as you see right here, for the throttle in relation to the map, the speed density. Now that being said, I gotta pull more out of the speed density because it's still rich, so I'm not gonna fuck with that throttle mass because what's gonna happen really is I'm gonna drop the speed density down and it's gonna be close to this throttle mass through this region. I'm gonna have a small gap in here. And so I'll have to adjust the difference pressure across the blade and a few other things to try and get the throttle air mass to follow the map a little better. But yeah, Matt, I think you were here when I showed the exhaust and ABCS intake changes, right? How much the exhaust made a difference for the reduction in VE and cruise, and the intake also did as well. I think the exhaust does a smidge more in cruise, but it is fucking nothing up top. And so I really think that the intake should have been done because you get EGR with the intake by adding overlap, but then you also get the increase in compression. Now obviously the EGR that you get with intake AVCS or VVT and overlap is based on sucking the exhaust into the intake port, whereas if you retard the exhaust cam like you're saying, then you can hold the valve open longer while the piston's traveling down the cylinder and you will get more exhaust EGR that way. And we did that and we showed that how 20 degrees of exhaust cam timing, only 20 degrees, made it change about 15% airflow or volumetric efficiency, and that's significant. And on the intake I did 20 degrees and I got like 7%. So the exhaust definitely provides more EGR than the intake. But I just was so mad at Chevy because I wanted to see it on the damn intake. Let's add some compression to get some more variable overlap in a way that benefits power and fuel economy too. Got some text messages here. Let me just double check, see what's going on. Those guys just bumped like 5 gallons of pump gas in here.
Is that better?
I mean, these things don't show until you turn them off and then sit for a while.
Oh, really?
Mm-hmm. Yeah, see, it still says 0. It's still in the gas light. There's a time delay in the cluster because they don't want, when you're driving and it's sloshing, to have your gauge go up and down when it's sloshing.
Oh.
So so they have a time delay on how fast it's able to change. And big changes like this tend to be ignored. So you have to turn it off, fill it, and wait a little while. And then when you start it back up again, the gauge usually changes.
Everything's flowing good?
I mean, it made 350 on 14 pounds.
Spent much timing in it?
It's about as much timing as it's going to use. Yeah. Yeah, there you go, quarter tank. The ethanol hasn't dropped yet. That's weird. It dropped some. Slow. Driving slowly. Seems driving too slow in my opinion. Speed this pump up really quick. The engine went brrr when I put the fuel at 100%.
Can I get your key from you so we can pull a couple cars where yours is at?
All right. I got the GTR controller in this car. Man, another 8%. We're close though. You see with 8% pull, the Lambda is just below the target, so it's probably going to be like 10% more. But holy shit, that's a lot of VE to pull. I mean, it's already at 90%. So we're saying that 80% VE up here. Does that make sense? Think about that, and I'll answer the question in a minute. Reduction in VE. So the short answer is yeah, actually, and in fact this whole area here that's really high is wrong. Because VE is not going to go up here. Like VE is not going to increase after a certain point. And so this whole section that's really high makes this area look crazier because it's not correct. A lot of cars, a lot of ECUs, I mean, don't use actual VE in their fuel mapping, in their fuel model. They use injector pulse width or other things like that that are inaccurate.
Where would you like your key, sir?
I say inaccurate, that's the wrong term. Just right there, my laptop. Inaccurate is the wrong term, I shouldn't use that term. It's not VE, basically. And they might mark it as VE or whatever, but it's not VE. And whoops, darn it. That was weird. Actually have, they use injector duty cycle and they call it, motherfucker, they call it VE, and it looks like this graph that always goes up, but that's not true. We talked about earlier pressure ratio across the engine, and I was talking how that affects the way it runs and how it affects VE. If you start adding in more exhaust gas, your VE is going to drop. Well, at higher pressure ratios, that's what happens with the engine. You can see here, VE's not going up a whole lot. What that is. Because in actuality, it wouldn't. When you add boost pressure, exhaust pressure goes up. Eventually, exhaust pressure can be higher than boost pressure, and you're going to start retaining more and more exhaust gas in the cylinder, and therefore, you lose VE. So, it looks wacky, but it'll almost plateau. You see here, it actually plateaus. If I have it at this angle, it looks like it's falling off, but really, it's plateauing, as you can see. And so that's actually going to be a little more accurate to what happens in the real world with the engine. This spot here, I'll probably never even hit. I don't think I'll even get the engine in this spot right here. 3,000 RPM and 20 something pounds of boost, not likely. But if I did, it would probably have a pretty high VE because the exhaust pressure isn't very high yet. It's a pretty efficient spot, unless we start surging the turbo or something. All right. I'm gonna change the cam timing. I'm gonna add 20 degrees right here. Just, no, not yet. First I gotta do a pull on that last VE map. Once you do a pull on that VE map, see where it is. I'm gonna add timing, I'm gonna pull timing and see what becomes of that. See if I can get the VE to come back up some in that area. I'm doubtful. Like I said, stock cams, it's kind of hard to do. Correction here, look at that, we got negative 3% near red line, positive 3% right here. Oh, I got 6% right there. Okay, 6% there, and that's it. So there's one spot through here, this region right here, I pulled too much out. So from 52 to about 65, I pulled too much out of it. So let's see where that's at in that fuel map. Before I do that, let's go to the blend table. We're in between the two tables right now, in the middle of them. So that means I gotta copy this one, put it over here, paste, which means I'm gonna be too lean now. Previously, before we had the pump gas, I was only on that VE table too, but we had a pump gas, so now we're at both. So I gotta add a little bit to this region. Unfortunately, now we're at two VE tables. I mean, I could change that parameter, I suppose, to put us back on one VE table. Do that real quick. There we go. So I'll start there. 1%, 1%, 3%, 3%, 3%, a little swing here. Positive, negative 3, but then it goes away. So one little spot right there. I'm not sure why it's positive. Oops, positive, negative right there. Let's double check the fuel map. There's something in there, but we can see now how close we are. I mean, maybe it needs a tiny bit of 5,000. That seems weird that it wants a little bit of 5,000, but it might. Let's get a little percent there. Okay. Alright, but you see that log there? That's very close. Gosh darn it. This touchpad is kind of ass. 1%, 1%. Here's 8% right here. So this region we need to add fuel. Right here. It's probably an area I pulled fuel out earlier when I was doing my smoothing. Yep. That is an area where I pulled some out doing my smoothing. My short-term and long-term offset each other, so that's good. That means I've hit the sweet spot there. Alright, so that's good. That's good. Air VE map, as ugly as that is, that's what the engine's doing. Let's do some cam timing real quick and see if it affects it any. Next, I'm going to do a big change, big intake change. I'm going to make this whole region here 25. 25. And then do a pull. We know we have about 1% or less correction in that loaded region. So we're at 25. See what the correction goes to. Correction went to -8, which means that was not beneficial. That was not good. So I think the dyno showed something similar too. Let me clear all these graphs off and compare the last two. Yeah, power dropped like a rock. So it was definitely closer before. I mean, I've done this before, right? So we'd hope that I was pretty close. Typically, we're running about 0 at 7. Some of these cars, you want 0 at 65 even. And then blend that guy into here. So what can I do to increase the VE down here? Or up here at the top end? I could try to check the exhaust cam. I don't know why I did that. That was dumb. I want this to be like that through here. And then right there. Let's check the exhaust cam, see what we got there. That isn't going to do it. That's really about where it's going to want to be. So what we're doing here is you're coupling expansion, or you're initiating exhaust blowdown earlier. exhaust blowdown reduces back pressure, coupling expansion increases power, and increases back pressure, right? So one lowers power and lowers back pressure, one raises power and raises back pressure. Typically is what you're looking at. So, but then by raising back pressure, you lower power, so that's why the exhaust kinetics almost no change on the top end, because both effects cancel each other out, unless you're just way off. And that doesn't look way off, but for experimentation's sake, let's change it. Let's just make it all zeros. Right here, we're seeing about 17-ish right now. We'll make this all zeros and see what happens. From -1 to -2, right? A 1% difference there with a 17-degree swing on it. Not that impressive. You can go back to this again. Typically on these cars we have like 17 or so on stock cams all the way to red line. It's typically where they are. Let's gonna do this. Oops. Oh, you know what? I should go the other direction just to see if it does anything, right? So let's make it bigger. 30 degrees all the way across. There, region 35 degrees or so. Actually helped a little bit. I'm surprised by that. That's not typical, but it actually improved. %6 even. Well, I didn't expect that. Did not expect that. Yeah, I got a 6% improvement out of that. Power showed it. Carried better to redline. Picked up about 20 horse at 7,000? No. Yeah, 20 horse from 65 to 7,000. I'll take it. Didn't gain anything there. To make that slightly less and blend that in. this low boost, the back pressure wasn't that high in the first place. So by not being very high, I didn't need to initiate a blowdown earlier. I was actually losing power by doing that because I was losing expansion and coupling. If this was at 30 pounds, it would probably have lost a lot of power there. And so I'm gonna, yeah, that's great. I forgot that we're not at full boost yet. We're only at 14 pounds. So up here, at the higher boost levels we're gonna run, that's where we're gonna have to run a lot less advance or retard on this cam. That's a big gain. That's way more than I thought it would gain. I like that. That's a surprise. I'm glad though, because I hate seeing that VE curve drop off like it was. So now I gotta add 6%. And that makes me happy. .06 multiply. Okay, let's check 6,000. Where was that at? 6,000 was only 3%. Okay, that actually works out because that's about what it's going to take to smooth that section out right there. Right here. 1.03 multiply. Look at that. Smooth it right out. This is probably a smidge too high anyways. Oopsie. That. Timing in that pull. Oh, and ethanol dropped too finally. Still made more power. Well, that's a lie. It didn't make more power overall. Peak power made more power in a certain area of the power band. Where power was dropping, instead of dropping, it flattened out a little more. Still made 352, but now it's 352 on 15% less ethanol. So that's a big bonus. Yeah, that carries way better. Yeah, I'm a lot happier with that. Alright, well, it's 5 o'clock. It's 5:15. I think we are done with this car for the day. See the timing, 24 at top, 17, 16 out peak. So timing dropped some as the pump gas came in. And decreased down there, but increased up here where the VE is dropping off. And then with the drop off in VE, we get a lower load calculation, which adds timing into it. So now we have a more representative timing ramp like a Subaru normally has. Yeah, it looks good. So I think that was good progress for today. I still have to add more boost to it, and then I have to put ethanol back in it. Then I have to set up the boost targets based on SI drive, because SI drive works with the EMtron. And then we'll have boost targets on SI drive and with ethanol. And then eventually he wants to get the screen that I've showed you guys, so he'll be able to adjust boost a little bit with the screen, as well as traction control, anti-lag, launch control, all that stuff. So other than that, I am done for today with this. We're gonna let it sit so I can check how good the idle control is on cold start tomorrow. Maybe tomorrow. I got a lot of stuff on my plate. So thanks for stopping by. Thank you guys for the donations. Those that donated, I greatly appreciate it. And I hope you guys all have a wonderful day.